Hi everyone. So we're looking at the product moment correlation coefficient between X and Y in the context of modeling of data. So we're told that PMCC between X and Y is 0.415. We're also told that the PMCC between M equal log X and N equal log Y is 0.764. Which model better fits the data? So here, definitely we're going to go for the model that reports the higher um, correlation coefficient, which is the log n m equal the coded model. So the log model is the model that we're going to go for. And from my introductory video, whenever we see log that corresponds to the 2L in the polynomial model. And the n tells us that we're going to use y equal ax to the n. So that's again just one way of trying to remember the functional form. So we can move quickly from here, from this to that form if we wanted to. But so where n is going to be the gradient, and a, so n is equal to the gradient, which is 0.9, and a is equal to 10 to the power c, which is 10 to the minus 3.6. So y is equal to 10 to the minus 3.6 x to the 0.9. And that would conclude part B. Now, some of you might feel that, well, I'm not sure if I can remember all of that. Let me just try to develop it from a first principles approach. So from a first principles approach, what we would do is we would swap n with log y and swap m with log x. So we would say log y is equal to minus 3.6 plus 0.9 log x. So once I have that, what I'd want to do is I would want to I'd probably want to group everything and group the log terms and then rearrange from there, use anti-log, and then solve for y. So I will write this as a power of x. So I would use the reverse power rule. So I would have log y equals minus 3.6 plus log x to the 0.9. So I bring the 0.9 up. Then I bring the log terms together so that it makes it easier to apply the log rules. So that's log x to the 0.9 equal minus 3.6. Now recall that if you have log y minus log x or log a minus log b, you can simplify it as the log of a over b. So I would write this as log of y over x to the 0.9 equal minus 3.6. And then once I have this, then I would write this in terms of take the anti-log of both sides. So it's assumed here that the base is 10. Now, one way that I do anti-log is this. I use a process that I call cross exponentiation. It's like cross multiply, but we now involve powers. So I do 10 to the power minus 3.6 is equal to y over x to the 0.9. So you can have your own technique. If that works for you, that's fine. So here, I will now continue, and I would have 10 to the minus 3.6 equals y over x to the 0.9. So this implies that y is equal to 10 to the minus 3.6 x to the 0.9. All right, so that accords with the result that I had gotten before. So whichever approach you are most comfortable with, then definitely have a go at that. All right. So in part C, we're asked to interpret the constants in the model n equal minus 3.6 plus 0.9 m. So let's clear some space. And then let's have a go at that. So do be aware we are dealing with the log-log model. So we can just do a sketch. So that would be log y and then log x. And then the gradient is 0.9. So essentially the argument is here that as m increases by 1, n increases by 0.9. So this is just the rate at which n is growing, 0.9. So the gradient will tell us that for every unit change in m, n will change by 0.9. Now sometimes the y-intercept is a nonsensical value, all right, meaning that it does not have any practical interpretation, but generally how we would interpret it in a standard fashion would be if m is 0, then n is equal to minus 3.6. So for when m is 0, n is minus 3.6. Another way of interpreting it is n is minus 3.6 is the value of n which is independent of m. All right, so that's another way of descriptively interpreting what it means. So when m equals 0, n is equal to minus 3.6. All right, and that concludes the presentation of this question.